Hello, I am about to walk you through how I generated all of these images of analysis, all of these animations of analysis associated with UAPs. And so I just wanted to show you some of the output of the analysis process we'll go through. These will take you through the technical steps you need to do to produce your own analysis upon your own footage of unidentified aerial phenomena, or actually anything that can be expressed as a pulsation of light. So I just wanted to show you these images, and let's dive in. So this is the video I produced. It has we go through 7 cases, right, of all these analysis and things like that. But I really wanted to share with you behind the scenes as to what's going on. So you might be familiar with the ETolemy software I've been talking about, which is visualizing the pulsations of geometry within the UAP from the Monroe Institute. And so this README here walks you through what I'm doing, why I'm doing it, particularly in that case. But we need to reproduce analysis. We need to look at multiple cases, and that's why I added this folder here, which is the UAP cases. Like I said, I walk through each of those cases of the application of this novel technique of unidentified aerial phenomena analysis. So I'm really putting forward that this is a novel technique that I've generated in collaboration with non-human intelligences through my dreams, and I've shared that story. But really, it's important to know that this is a novel technique being applied to unidentified aerial phenomena. And so I'm just describing it here. I'm offering all of my analysis files that I used to generate that video, as well as the data here. And here is the README file, and I just want to walk you through that README file, the files in the folders, as well as what this looks like, so you can do this analysis, and so we can start figuring out what these flashing lights in the sky are. And so the steps here that you really need to become familiar with, and this will make sense as we go through, are the isolation of the UAP in video editing software. I use OpenShot. Then the generation of images from the isolated video of the UAP. I use ffmpeg in the command line, and I'll show you how I do that. Then you do the analysis of the images. So you get the brightness of that UAP, you get how wide of a brightness or intensity difference there is between darkest dark and lightest light. I get the max. I'm using the Python image library in the context of a Jupyter notebook. Then we'll go through the analysis of contour detection or object detection, so we can start to describe the XY coordinate in the frame, as well as get the area of the pulsation. And then finally, we write to a CSV file. We then generate we generate analyzed frames for the animation, and that's one of the parts of the method here, is the actual demonstration of geometry. It's not just the production of numbers, it's the demonstration using multimodal, that's sight, that's numbers, that's sound, of the geometric properties we're seeing, so we can really start to use our the original intelligence, right, like natural intelligence, to do pattern detection. We don't need to rely upon machine learning algorithms and AI in this case, because we can see, feel, hear these patterns. And so that's part of the analysis method here, is the generation of multiple different ways of looking at the same pulsation. And then finally, we visualize the CSV data through the kind of traditional graphing. In this case, I would say the novel aspect of the technique is the selection of the x-axis as the frames, as well as the vertical axis as one of the measures we've defined already, expressed in a proportion that you can see the visual differences, right? And you can measure them with your tools of drawing and sight. This whole thing requires familiarity with programming in Python. You'll be surprised to learn that most of the code actually is 14 lines long, 18 lines long. I'll show you that shortly. And it's not a lot of code to do all of this analysis, actually. So you can learn all the Python you need to start analyzing and doing this work in probably 4 to 8 hours. I'd recommend starting with a Python tutorial from W3 Schools, then learning about Jupyter notebooks focused on data frames and how to do that. And then I would look into the Python image library and the OpenCV documentation. My own development environment, which you're seeing projected in the background of this video, is based in Windows 10. I use the Ubuntu subsystem, the WSL thing they have going on, generally in the context of Visual Studio Code. I use GIMP for image creation, OpenShot video editing, ffmpeg to extract the frames from the videos, Jupyter Notebook, Classic for the Python 3 programming, Python image library, and OpenCV for image analysis. Then I use Tableau Public for data visualization, and ImageMagick for the GIF creation, and OBS Studio for video presentations. And if you are observant here, all of these tools are open source and free, which this library and this technique, this novel technique of UAP analysis, I'm offering as open source under the share-alike non-commercial Creative Commons license. Like I said, so I'm going to talk through these sections. You can skip around as you need. But we start with isolating the UAP in the video. And I'll show you that. Let's show you that right now, actually, because that's helpful to know. So in this video example file, we have Cosmic Highway, the video I pulled from the internet. We have a mask that maybe we can click in and see what that looks like. But you see there's a transparent circle that is in the center of that frame. And then we have a cosmic.osp file. If you open that up, it'll probably say, hey, we're missing files. Where's the directory? You just point it to that video example directory on your local system, and then the OpenShot should work. This is an example of what it looks like. So what we're doing here is I'm taking this, and if I go back to the beginning, I will show you 0.05, shifting down the alpha of this, meaning I'm making it transparent, and you can see that on this side here. And then I think I have to play this for us to get, transparent. You can see it transparent, and I keep it transparent. And what I end up doing is I follow this guy, and then and you can see the mask is moving, that circle is moving to follow it. I just go, I watch it, I move the circle over it, I pretty much go frame by frame. Monroe Institute was wonderful. I didn't have to move it at all. This one I have to move it some, but a lot of these footages have about 10 to 5 seconds of really good, sort of, it's right there, and then with a little bit of movement around, so you can see all of the keyframes I've added here. And then generally I go back to the beginning to bring the alpha up to 1 before I export it, and I just export the file to video here. So that's what it looks like. You can do that yourself for the footage. It's a very simple technique, so I don't think I need to explain it much further. The only other thing to keep in mind is when you move the keyframes around in OpenShot, it has a sort of blur or Gaussian kind of bezeling or whatever to the transition. I use a constant transition, so I know exactly where that is, and I know for a fact, because I've looked at every frame, that the UAP is in kind of the center of this circle. In terms of this circle right here, it just needs to be kind of in there. I believe I've moved this since the example, but it just needs to be in the frame because we're doing analysis across the whole frame. The only other decision you need to make when you're doing this is if there's multiple sources of light in the circle. we need to then make sure that the object detection in the next steps can really pick up on the UAP and is not picking up on the other things. So you might have to be a little creative as these things move around the stars, but if you can capture the UAP in that circle, you're good to go. So that is the video example. So we'll go back here to the README file. Next thing you need to know about are these command line prompts. So after you generate the image, you'll have a video file. After you generate the video file, generally crop that to where you want to do the analysis, generally where you don't have to move around that circle too much. You then have to generate the images for each of the frame. And so there's a few ways to do this. I started with like an add-on to VLC open source video player, but that was indeterminate, meaning it would sometimes produce 1,000 images, sometimes 1,003, sometimes 995 for like 1,000 frame video. And we really need kind of determinate activities happening here. So ffmpeg seems to do that. I generate the frames and into the folders, and you'll see the folder structure set up. The only other command line you need to do, aside from starting your Jupyter notebook, which you'll learn about as you go, or you already know about, is using ImageMagick to convert all of the GIF frames into a GIF itself. And I do that. I think there's programmatic ways to do that. I do that through ImageMagick just because that was the first method that came up when I Googled it. And those GIFs are sort of a way for me to test and as well as look at what is happening. So we'll cover that, that whole process shortly. Here's the cases that are in here. I linked to the original video, any other relevant videos or whatever, as well as data. You can click in there to the data if you don't want to deal with GitHub or anything, to just get the data, right? This is the interactive Tableau public dashboard. Navy Pyramid is a plane, and you can really get everything you need by clicking on that download. You can get an image of this chart, you can get the data, a PDF, or the Tableau workbook, which is really cool. So you can start building data visualizations already off of this data, or get the data directly in a click way as opposed to a GitHub sort of way. All right. And once again, this is licensed. This is intellectual property. And this is this novel method of unidentified aerial phenomena analysis based upon the ruler and compass geometry analysis methods that I've been using. This is intellectual property. This is a novel form of analysis. This is something like a trade secret, perhaps, that I am now sharing and publishing pretty much within the week of discovery, primarily because this belongs in the belongs with the public, for the public, in a sort of Creative Commons way. So I understand this to be an expression. In this little bit, I'm saying I am taking all ownership I can of this technique in order to then publish it as a Creative Commons open source technique, right? Because you'll see the code itself is like 14 lines long, and I just want to make sure that this always remains publicly available, free of charge, to use this form of analysis to really bring this science and whatever could emerge out of this into the public domain that is based in this sort of free and open collaborative way of engagement and discovery. So having walked through the walkthrough, I just want to walk through some of these files. So in each of these folders, we will see a few things. One is the video, one is the CSV analysis, one is calibrate Python notebook, and one is an analyze. And so each of these pretty much have the same situation. you might need to create a folder directory to get the scripts working, but it should be obvious what will happen. So this is what you do in each of these folders, and I'll just walk you through this now. So this is Jupyter Notebook. It runs on my local server, and it shows a directory here. This is Jupyter Notebook running in the ETolemy directory. And so you can get to the analysis of the Monroe Institute, the specific ones in here. But I added this folder so you can click in here. And so I'm clicking in here, and as you can see, we've got here the frames folder. It's got a bunch of frames in the, I think I added that folder to the git ignore file. So you'll see those in the repository shortly. There should be 100 frames per folder, or 10 as a sample for you to get into. But I want to just show you this because it starts any of the process after you get the video in, after you get the frames in. So we've got the frames in the folder generated from the ffmpeg command. We've got, then we open up this. I basically copy and paste this file to each directory as I go. And we can then change, I say, I want to test frame number 15 to see what it looks like. And so now I'm just testing to see the analysis process, which is brought in here. This is primarily just to get the object detection for Python's OpenCV library working. As you can see, it's identified the center of the object here, as well as drawn the circumference of that object. And it does so through a couple of analysis processes that are relatively easy to mess around with. Generally, what I change is this sort of blurring experience. Let's see, I can do that there. And then down here, I change this value. So that, and sometimes I change the other ones, but generally this is what I've been messing with to really calibrate the object detection. Sometimes that needs some specific calibration because sometimes it detects a lot more, sometimes it'll detect the whole circle. That's why this process is a little bit why we select the background of the mask image to be kind of similar to the sky. All right, so it's showing off those images. Once you get a good understanding of the calibration of the object detection, we can come back into the analysis experience. Same code, same very similar code. I copy paste it. This is it. This is all of the. This is it. This is all of the code. I guess it's more than 12 lines, but it's very close to, it's like less than 50 or so lines of code. It does all the analysis, and so basically for each of the frames that are in the frame folder, we're going to analyze the frame. That analysis here, we get the file into the Python image library, and then we use that to get the brightness, the valence experience, as well as the max of the brightness. So that's what we're using to get the very basic measures out of it. And then we're using object detection in the CV, the OpenCV Python library. We're converting it to gray. We're blurring it out like their documentation says. Just follow their documentation. This is what I did here. Then we're finding the contours of within the images. Then here we're iterating through those to figure out which is the UAP or not. And then once we figure that out, which is pretty simple to do, it's generally the second largest object detected in the frame that we produce, which is why we have this contours in the -2 index. So then here we're drawing the contours onto the image, meaning that kind of border of the circle. this is where I change, if it's like the navy video, I had to change it to blue. This is where I changed it. Then I'm adding text on top of that image in order to generate the frames of the animations you're seeing. This is a really helpful process to me because when I'm analyzing and looking in it, I'm also, let's pull up, I'm also like testing. I'm going, oh, that looks like a peak there. Let me actually go into this folder. And this is generally what I end up doing. And I look here. And then I say, oh, okay, I see. I understand what's happening. I understand what's happening because I can see it. And I just use the frame number pulled from the Tableau public. Like I would look here in the dashboard. I go, oh, that's frame number 93 or whatever. Then I come over here and I find the frame, and then I'm able to sort of just go backwards and forwards and just see what that looks like. And that's a really helpful thing for me. So that's what I've been doing. Let me see what else here. We were going through this process, the analysis process. Yeah. And then I'm just basically saving the frames, saving the large frame to a folder, and then cropping that in to make frames of the GIF animation. I think here I'll add in some automated way of doing that in the Python notebook. But for now, it just outputs to a directory. And then it writes all of this data to a data frame. And then at the end of this, you can write that data frame to CSV. The Tableau public dashboards drive directly to that. Here's the Tableau public dashboard. Tableau public's free. Basically, it's Tableau, but it saves to the cloud, and it's the things you save are public. So, which is good when you're doing open source and open data work. So here I've got one sheet, basically. I just wanted to point out a few things. The only thing you need to do when you bring in the CSV to the Tableau is ensure that you're working with you convert the frame to a, dimension, and you make sure it's continuous. And then you can draw that in, drop those in. I also ensure that all of my marks are black because I print them out and that the path actually is step and not linear, primarily because we're working with discrete information with the frame number as opposed to an actual continuous sort of line. That's the sort of change I do. And then from here, I take the sheet, then I drop it onto a dashboard, and I change the size of that dashboard to something I can print out. And then I save it to Tableau Public, and then we have these that you can start to work with. I use as the analysis, and that's why. So we're getting many different ways of getting data out of this pulsation, and this is one of the ways. I just wanted to show what else. I think that's it, right? Because when we go into this GIF file, the analysis produces all of these frames. And then what I end up doing is navigating to the directory, and I use this command here to just generate the GIF. I had to change some configurations in the ImageMagick to have enough memory to produce these things, but that's pretty simple. So then you have the GIFs that are available there. I just wanted to see if there's anything else you need to know. We've got all of the cases I looked at for that video here. We've got the README that gives you the instructions, the video example to produce that, and we've talked about the license of this novel technique of UAP analysis as open source. So I think we're all set and ready to go. Please, yeah, look into this. Stay in touch. I think this analysis is very potent. It's very, very potent, primarily because, as you can see, right? You can just hold all of the whole thing here is actually 235 lines, including all of this stuff. So it's like not a lot of lines in this situation. So of code, you can read it really easily. You can track all of the analysis by looking at the files. And so it really should establish a geometric demonstration of some of this anomalous mathematics that's coming out of UAP footage. Anyways, once again, thank you. And I hope that you just discover the most magnificent things through this experience, as well as go on a journey of discovery as to what the other dimensions of signification are here, right? Because if they're revealing this geometry, we have to then deduce that there are many other dimensions of meaning being revealed that may not be so objectively understood. And in that way, we might actually invite this multimodal expression or exploration into all of that beautiful tapestry of meaning simply by looking at the numbers, by analyzing it, by debunking videos and things like that, by encountering orbs in this way, right? We might start to invite a sense of more expression of these different dimensions of meaning, right? So as you look at this, you might have an experience of connection with the geometry itself. You might have an experience of a connection with the orbs or, and I'll just show you, these are the orbs, right? This is what connected with me. The one above my head here is a plane, right? The one above that too is a plane. So, but the rest of them, maybe something's going on. But the reason why I'm offering this and saying it's so potent is even if all of these turned out to be planes, the geometric exploration and the mystery and the inquiry involved is actually meaningful in and of itself. The geometric expression, the geometric inquiry will bring you in contact with intelligences that are inlaid within this fabric, the fabric of our reality, that are expressing through these many different modes of geometry. And so that's what I really hope you discover in this exploration. And that's why I'm offering all of this stuff, all of the analysis technique. And yeah, may this all be of benefit to the earth and to our human family. That's really the prayer. May it be of non-harm. May it be of benefit to you, your community, and the earth.